Welcome back, students. Let's resume our problem. We've been doing this problem. We checked out we had regular singular point at t equal to 0. And thus, we apply Frobenius method. That is, power series expansion times t to the rth power, eventually generating t to the n plus r power instead of just t to the nth power. After that, pretty much the same. Derivative, the second derivative. From the original equation, with just a little bit of algebraic manipulation, and let's plug those in. Red is the second derivative, blue is the first derivative, green is the original, and we have two originals here because we have this and that. Now pass on t squared, generating t to the n plus r power. Pass on t, generating t to the n plus r power. This one is originally t to the n plus r power. Great. Now finally, this one is problematic because if I pass on n plus r plus 1 power, we have a bit of a problem. And this is something we have to work on. How do we work it out? Here we go. This part, which I'm highlighting in bold, rewrote in this brown color, okay. And then let's apply the index shifting. We want this n plus r plus 1 to be n plus r power. So how do we do that? We take the index shifting n by n minus 1, so that this one is n minus 1 plus r plus 1, so that we get n plus r power. Good. Because I replace n by n minus 1, I have to do the same thing everywhere whenever n show up in this brown series. And eventually we end up with this. N is going from 1, and I see n minus 1, and t to the n plus r power. Okay, now let's resume here. Unlike the previous case when we had ordinary points, I cannot change this summation just blindly into n going from 0. It doesn't work this way. We have to consider n equals to 0 case separately, and that generates appropriate r value. Now, these three series begin from n equals to 0, but not this one. So when n equals to 0, the contribution from this brown series is not there. Therefore, we get this expression here. This part, which I'm highlighting bold brown, contributes nothing here. N begins from 1. So when n equals to 0, this part doesn't do anything. How about red, blue, and purple? Plug in n equals to 0, and then you're going to get these coefficients. Plug in n equals to 0, so we have 0 plus r, 0 plus r minus 1, and then 0 plus r, and so on and so forth, and we get this equation. And let's work out a little bit. This part, just throw that away, and then we can simplify out C0 from each class, because if C0 is 0, then it'll turn out everything is going to be 0. We have trivial solution. So factor that out. And then further factorization. And what do we get? We get this. R equals to 1, which comes from this factor, or R equals 1/2, which comes from the other factor, or C0 is equal to 0, which will generate a trivial solution. Trivial solution, what do you mean by that? All the coefficients, let's go back here, and C0 is 0, then it'll turn out that from recursive relationship, C1 is also 0, C2 is also 0, C3 is also 0, or 0. So y is just constantly 0, in which case, trivially, this equation holds. So we have a solution, yeah, but that's not really a good solution that we are looking for. when r is equal to 1 or r equals to 1/2, we need to do some work. And then when r equals to 1, we're going to get one solution. R equals 1/2, we're going to get another solution. These two solutions will have to be linearly independent, or you can check those out with Wronskian or check out the collinearity, if you will. And if you get those, then you can write the general solution as a y1 plus b y2 or things like that. In any case, these two are the eigenvalues that we are looking for. Another key characteristic, the difference between these two is a fraction. And if they're all integers, then we're going to be in trouble, actually. And that'll turn out to be type 2, type 3, those harder cases, which I'm not going to talk about in this review session. So for exam level, I think this is going to be sufficient. Yeah, after all, I'm the one writing the exam problems, so I don't think I'll have to overemphasize this. So in general, you're going to get r equals to some fraction or r equals to another fraction, and the difference is going to be non-integer, so that you don't really have to worry too much about the ramification down the road. In this case, it fits perfectly. R is equal to 1 or r is equal to 1/2, and that was not too difficult to solve. It was just a quadratic equation. Yeah, just remove the C0, and then we just have a quadratic equation to solve. Okay, we got our values, and we have to consider the recursive relationship here. All right. Where were we before? Yes, this was the series expression we got before. And then when n equals to 0, only these three series contribute, and then we did those, and then we got this conclusion. Okay, so when n is 1 or greater, then we have all four series coming into play, and we're going to end up with this equation. The red series gives me this coefficient, and then blue series gives me this coefficient. Purple series gives me this solution, this coefficient, excuse me, and then the brown series gives me this coefficient, Cn minus 1. And putting everything together, we have this recursive equation. And what we need to do is solve for the higher of the two. I'm solving for Cn with respect to Cn minus 1. Let's go ahead and do that. Let's factor Cn out with a bit of an algebraic manipulation. Put those two together so that you get this expression. And then please note that we have n plus r minus 1 common to both. So factoring those out, then we get further factorization like this. And then solving for Cn, you have the recursive relation. If you're unsure about all these, then throw that part away, and then just form a quadratic polynomial, and then try to factor it back. It'll work. Okay, let's recap just a little bit, all the way from the beginning. This is the equation, and then I'm not going to check again, but this will turn out to be a regular singular point. Okay. So let's take a power series expansion, not just a power series, but multiply t to the r power so that we get t to the n plus r power. This is the essence of so-called Frobenius method. And take the derivative term by term, take the second derivative again term by term, and plug those into the original equation. The color coding will help you. If you do that, you're going to get this expression, and let's do a bit of an algebraic algebraic manipulation, excuse me. Pass on 2 inside, okay, that's fine, and t squared inside, and that'll change this power into t to the n plus r power. Great. Pass this times t, and this will change into t to the n plus r power. Again, great. This one was t to the n plus r power to begin with, no problem there. Now pass on this t into this, and we get t to the n plus r plus 1 power. We have a problem. We need index shifting. Go ahead and do that. This one becomes the finally like this. Cn minus 1 t to the n plus r power, where n is going from 1, not 0. Now for ordinary points, you just change all this into n going to 0, and then you can go from there, because and in the end it turned out the difference was 0, but not anymore. For regular singular points, you can't do that, and you have to consider separately. You have to work out n equals to 0 case separately. If you do that, case 1, n equals to 0 case, we get this recursive relation where brown part does not contribute, there's nothing to add, so that's 0. And what do you have? All these have C0 in common. So factor those out and do a little bit of algebra, and then what do you get? You can factor this quadratic trinomial, and then you end up with this factorization. Eventually you get r equals 1, r equals 1/2, or c equal to 0. The last case is a trivial solution. What if you have a complex numbers there? No sweat. Just r value is going to be that complex, and that's it. No problem there. Now, n is greater than or equal to 1. In that case, we need all 4 series. And then this brown part generate this part. And then let's solve for Cn. How do you do that? All these have Cn's in common, so factor those out. And we end up with this, with some work. And eventually we end up with this recursive relation. And that's how we got this.